Greetings and welcome to the complete lecture for Chapter 4, Sections 4.4 through 4.6 of Chemistry 150. I'm glad to have you here. In this video, we're going to follow what's called the Lewis structure and see the advantages that it has for chemists. A Lewis structure is great for telling how electrons are distributed in a molecule, and a Lewis structure can also be coupled with something called VSEPR to understand the geometry of the molecule and to get some insights as how they react. So without further ado, let's check out this section and see what it has to offer. First of all, we're going to look in this section mostly at what's called a covalent bond. And in a covalent bond, you have sharing of electrons with each other. So this is different from when you have metals and nonmetals coming together because they tend to actually have an electron transferred from the metal to the nonmetal. So the metal becomes positive usually and the nonmetal becomes negative. Covalent bonds are usually between nonmetals and they form a sharing. So it's not as strong of a bond as an ionic bond, and at first that might seem a disadvantage, but actually sharing of electrons to make covalent bonds is what we need for life, because in life we need to have lots of reactions really quick, and a covalent bond fills that bill perfectly because it allows for reactions to occur quickly without too much trouble. An ionic bond would take a lot more energy. We're also going to see how a lot of times when a covalent bond is made, it ends up creating a type of a noble gas configuration. And a noble gas configuration is something we'll talk about in another chapter, a little bit more detail. But a noble gas basically means you're going to have 8 electrons around it. And because we'll be dealing with pairs of electrons, we'll usually be talking about 4 pairs of electrons. So remember that a pair is 2 electrons. 4 pairs times 2 electrons would be 8 electrons. That'll be the noble gas configuration. Here's an example of a covalently bonded molecule, and it's probably the most famous of all of these, which is water. You've probably had water to drink already, or in a cup of coffee or soft drink or something like that. Water is H2O, and when you combine 2 hydrogens with 1 oxygen, you create the molecule there on the right-hand side. And if you look at that hydrogen-oxygen-hydrogen combination, you can see that the water, it's kind of like a V. And we're going to discuss in this section why that is. But anyway, to figure out that this is covalently bonded, water has only nonmetals. And just as a quick review on the periodic table, everything to the upper right of that metalloid line is considered a nonmetal. And that does include hydrogen, although really technically hydrogen is on the left side, but hydrogen's kind of the trip out here. So hydrogen plus all those nonmetals, that's what we're going to focus on a lot in this section. And those, when they come together to make molecules, will create covalent bonds. So here's a question you can test yourself to think about if these molecules are bonded through ionic or covalent bonding, all right? And again, the punchline here is that in an ionic bond, you usually have a metal and a nonmetal. So in the first one, PCl5, both phosphorus P and chlorine Cl are both up and to the right of the metalloid line on the periodic table. So we would guess that PCl5 is covalent. It has all nonmetals in it. But the very next one, which is a combination of sodium, Na, and oxygen, sodium is a metal. Sodium is to the left of that metalloid line a long ways. Anything with a metal we will predict will be ionic. You've got metallic sodium with non-metallic oxygen. That's going to be the classic combination for an ionic species. The next two are kind of interesting. Now the first one is SO3, and that has sulfur and oxygen. Both sulfur and oxygen are considered nonmetals. They're up and to the right of the metalloid line. That would definitely be covalent, all right, because you have all nonmetals. But the next one has a calcium in front of it. And remember what I said earlier, calcium is a metal, all right? And calcium, a metal, is not reacting with SO3 that has covalent bonds. It's actually combining with sulfite. SO3 2- is one of the ionic species that we saw with the polyatomic ions. So again, anytime for us anyway that you see a metal with anything else, basically, it's going to be ionic. That calcium is going to make it be ionic. And this last one in here I threw in just for fun. Antimony and arsenic are right on that metalloid line. And it's honestly hard to say sometimes with those if they're going to act like metals or non-metals. So for this one, I wouldn't even probably know myself. I mean, if I had to guess, I'd say, well, antimony is probably more metallic and arsenic probably more non-metallic. But man, metalloids go both ways. They really do. So this one would be difficult to know. And I wouldn't ask you ones like this, but hopefully it makes you think about when you have ionic versus covalent. So again, ionic bonds have metals, covalent bonds have just nonmetals. The nomenclature, which we talked about in the earlier lecture, of covalent compounds is different than the ionic compounds. And when you have a covalent compound, you can use the Greek prefixes. So for example, CO2 is carbon dioxide. PCl5, that first one up there, would be phosphorus tetrachloride. When you have a metal with a nonmetal, you're either going to call it just metal, nonmetal oxide, like sodium oxide, or you could have sodium chloride for that matter. Or, of course, you could use the Roman numerals if you had a variable charge transition metals. So that's why this stuff becomes kind of important. It's a different kind of bonding, and so chemists need to know if it's going to be strong bonds like ionic bonds or weaker bonds but more flexible bonds in covalent bonds. Covalent bonds, as I said, can generally form between nonmetals and other nonmetals, and there's a whole bunch of different kind of compounds that can be made. At first on the periodic table, it doesn't look like there's very many nonmetals, but in reality, those nonmetals bond in all kinds of different ways. And so all of our body is almost all covalent bonds, so DNA and all that kind of stuff, the CO2 that comes in, water, lots and lots of examples. And the metal compounds have specific purposes, but they're not as used quite regularly. So let's go back to water again, H2O. When you draw a Lewis structure for water, the hydrogens are on the outside of the oxygen, and the oxygen actually has two lone pairs on it. Lone pairs are drawn as dots, so you can see there's one on the top of the oxygen and the other one on the bottom of the oxygen. So oxygen has more electrons around it than hydrogen does. Here's a Lewis structure for ammonia. Ammonia is NH3, and you can see that sure enough, that nitrogen has a lone pair on it as well. So nitrogen has 3 bonds to hydrogen and 1 lone pair. So these are examples of Lewis structures. And just right away, you can see that that central atom, the oxygen and water, or the nitrogen in ammonia, they have more electrons around them than hydrogen. And this is the kind of information that you can get out of a good Lewis structure. In most covalent molecules, each atom is sharing enough electrons to create a noble gas configuration. Now again, in a nutshell, noble gases basically mean 8 electrons around them. So if you look, for example, at the oxygen down there, oxygen has 1 and 2 lone pairs, and each of those is 2 electrons, so that's 4 electrons. And in addition, these lines right here are called bonding pairs. And bonding pairs also have 2 electrons. So there are 2 plus 2, 4 electrons from bonding electrons with hydrogen. And oxygen also has 2 plus 2, 4 lone pair electrons. So that's a total of 8 electrons, or 4 pairs. That's going to give it its noble gas configuration. Now the nitrogen on the right-hand side has the lone pair like we talked about, and it also has 1 and 2 and 3 bonding pairs to hydrogens. So 3 bonding pairs times 2 electrons per pair is 6 electrons, plus the 2 electrons as the lone pair. It also has 8 electrons, which is a noble gas configuration. Hydrogen only needs to have 1 pair of electrons around it. And at first you might think, oh, poor hydrogen, it's not getting a noble gas. But helium, which is right next door to hydrogen, by the way, has only 2 electrons. So hydrogen does take a noble gas configuration, but it's like helium. So just realize hydrogen only needs 1 pair to be happy to have a noble gas configuration. But most of the other atoms we're going to see need a full noble gas configuration, which means 8 electrons. And it can be through a combination of bonding pairs and lone pairs. And again, finally, each pair has 2 electrons on it. So here's an example of the periodic table. Some of the nonmetals we'll see a lot in this section. And it kind of shows the number of bonds and stuff that are going to be around things. Now, for example, oxygen up there in the kind of top middle, oxygen, it says, is going to have 2 bonds around it. And 2 bonds would be 2 bonding pairs. And that's okay for oxygen because oxygen also has 2 lone pairs. And right left of oxygen, we see nitrogen. Nitrogen likes to have 3 bonds around it usually. Nitrogen's okay with that because it has 1 lone pair. So most of these will have these number of bonds to be happy to have this noble gas configuration. Again, hydrogen's kind of the exception. It's only going to have 1 bond because that's all it needs. But the other ones and stuff are going to do it. Now, we're going to talk about this here in a little bit, which is the number of valence electrons. And the number of valence electrons is, first of all, equal to the group number. So if you were curious how many valence bond electrons fluorine has, you would look at that 7. And that 7 means 7 valence electrons. Now, fluorine has a total of 9 electrons, if you remember from an earlier lecture we did. This 9 electrons total in fluorine, not all of them are available for bonding. So the 7 there represents the number of electrons which can be used for bonding. The other 9 minus 7, or 2 electrons in fluorine, are considered core electrons and they don't bond. So just realize it's only the outer electrons that bond on these molecules. Likewise, for example, carbon, which is number 6 on the periodic table, has 6 electrons total, but it has only 4 valence electrons because it's in group 4A. So 6 minus 4, the other 2 are just core electrons. So valence electrons represent the number of electrons which are available for bonding in the molecule. And that's going to become really important to us. And the number of valence electrons equals the group number. And everything in the same group is going to have the same valence electrons. So for example, we talked about fluorine earlier, fluorine having 7. Well, chlorine right under it, chlorine is also in group 7, so it has 7 valence electrons. And so does bromine below that, and iodine below that. So everything in that group has 7 valence electrons. And the same thing for the left, group 6A, they all have 6 valence electrons, etc., etc. Now, group 8A doesn't usually react at all, so that's why they're saying 0 bonds. The noble gases are very, very stable. In other classes, we'll look at some expanded valence kind of things where they can, like krypton and xenon can, but it's rare, all right, and they're more interesting intellectually than as a useful process. So to summarize this slide, the number of valence electrons equals the group number, and that's going to be important for us coming up. So here's a question you might experience. It says, how many valence electrons in phosphorus, which is P on the periodic table? Now, phosphorus is number 15 on the periodic table. And by the way, I do recommend that you have a periodic table in front of you. You can get a good one at mhchem.org/pertab, P-E-R-T-A-B. If you can't find it on the web, I'll find one for you. But anyway, phosphorus has 15 electrons, but remember, not all of those are going to be involved in bonding. We're only looking for the valence electrons, the ones that are involved in bonding. And if you look at the periodic table, phosphorus is in group 5A, and the 5 is what we need. So phosphorus has a total of 5 valence electrons. The other 15 minus 5, 10 electrons are considered core electrons, and they just sit there. They don't react in making molecules. When you're making a Lewis structure, you can make single bonds and double bonds. Now, a single bond is a single line, and in the Lewis structures we've seen so far, it's always been about just single bonds, all right? But sometimes it's nice to make double bonds. So remembering that carbon likes to have an octet, which is just a fancy way to say 4 pairs around it, you can see that carbon with a double bond to oxygen there has 4 bonds. It has 1 bonding pair to this hydrogen, 1 bonding pair to that hydrogen, nitrogen, and there's 2 bonding pairs to oxygen. So a total of 4 pairs. Now the oxygen is not being ripped off or anything like that. If you look at the oxygen, it has the 2 bonding pairs to carbon and 2 lone pairs for a total of 4 pairs, which again is the octet. So that's an example of a double bond, a multiple covalent bond. You can have more than one bond between atoms, and a double bond or even a triple bond are possible with Lewis structures. Here's some examples of double and even a triple bond. Carbon dioxide, another famous, unfortunately, covalently bonded molecule, when you draw its Lewis structure out, is a carbon with a double bond oxygen on the right and a double bond oxygen on the left. So this is the Lewis structure right here, and you can see the double bonds. Now, the actual structure, which is this blobby thing right there, just shows the oxygens kind of squished together, and they're useful in terms of where the electrons are, but they're not very helpful in terms of the strengths of bonds and stuff like we'll see. So sometimes when people are creating these structures, they'll start with structures like this, but please don't use this as your structure. You want to use lines for bonding pairs. You want your Lewis structures to look something like that. But anyway, carbon has a double bond O to both the left and the right of it. And again, carbon is sharing 4 bonding pairs, which is 8 electrons, octet, it's happy. And the oxygen each oxygen has 2 lone pairs and 2 bonding pairs, 4 pairs, again, the octet. N2, nitrogen, which you're breathing right now, the air we breathe has a lot of N2 in it. When you draw the Lewis structure for N2, it looks like that. It has a triple bond between the 2 atoms. Now, nitrogen on the left is sharing 3 bonding pairs with the other nitrogen, and it has 1 lone pair. So again, 3 sharing plus 1 lone, 4 pairs total. Guess what? That's got the octet again. N2 is very, very stable, and the other nitrogen is in the same environment. So double and triple bonds are totally possible. It is possible to have what's called a quadruple bond, a 4 bonds system, but those are usually between metals, and it's a very esoteric kind of weird thing. But it is possible, although we won't see them in Chemistry 151. Molecular formulas and structural formulas are a good thing to talk about here real fast. Most people, when they talk about water, they say H2O. That's the molecular formula, and it shows how many atoms are in there and stuff like that, which is really cool. So H2O is probably the way you've talked about water, which is great. Sometimes it's useful, though, to think about what's called a structural formula. And when you want to know where the electrons are existing in a molecule, a structural formula is better. So in reality, like we saw earlier, the oxygen is in the middle of the hydrogens. So HOH is a better version on some levels. This is called a structural formula. It gives you information as to what the molecule looks like. Now, honestly, most of the time, chemists will use molecular formulas because they're more condensed. They don't take up as much space, etc., etc. But for Lewis structures, often you will see a structural formula showing the connections between the outside atoms and the inside atom or atoms. Lewis structures will show both lone pair electrons and the bonding pair electrons, and they always use valence electrons to make it happen. So the lone pairs, again, are just little dots. Please do not draw anything but dots for lone pairs. Don't draw lines or anything like that. Lone pairs are those dots. Bonding pairs, on the other hand, will be drawn as lines. They'll have a line. So in the water molecule, like we talked about earlier, there are 2 lone pairs, and we represent them by dots. Go dot, 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 dot. And bonding pairs, on the other hand, are drawn as lines. The bonding electrons are shown that way. So each line you draw, again, is 2 electrons. It's not just 1 line or 1 electron. It is 2 electrons. And that gives oxygen in the middle, its octet, all that jazz. So it's helpful to know the connections that are common between the central atoms when you're drawing Lewis structures. And I've given here examples of some of the more common ones we're going to look at. Carbon is very happy with structures if it has 4 bonding pairs around it. Now that could be a double and 2 singles, like we saw in the example earlier, or it could be 4 singles, but that's a very, very common thing. Nitrogen, we saw with ammonia earlier, nitrogen has 1 lone pair and 3 hydrogens hydrogens around it in ammonia, that's nitrogen with 3 bonding pairs and 1 lone pair, and that gives nitrogen a very stable configuration. Oxygen, like in water, likes to have 2 bonding pairs and 2 lone pairs. So in water, it was 2 single bonds and 2 lone pairs. Once in a while, we'll see that oxygen likes to have a double bond and 2 lone pairs, but those are common configurations for oxygen. The halogens, which are group 7A, so this would be fluorine, chlorine, bromine, iodine, etc., they like to have 3 lone pairs and 1 bonding pair, and we talked about earlier how hydrogen is happy with just 1 bonding pair. You'd never want to put a lone pair of electrons on hydrogen or make double or triple bonds. Hydrogen can only handle a single bond. So let's draw a Lewis dot structure for ammonia, NH3. And I showed it to you earlier, but I want to show you where this comes from. So the first thing you want to do with ammonia is you want to count the valence electrons. So ammonia has 1N and 3H. Well, nitrogen is in group 5, so it has 5 valence electrons, and hydrogen is in group 1, so it has 1 valence electron, but there's 3 of them. So because the nitrogen has 5 and hydrogen has 1, and there's 3 of them, there's going to be 8 valence electrons in NH3. Now, most of the time, like we've seen, pairs of electrons are the way to go. So 8 divided by 2, most of these will have, or this particular molecule, will have 4 pairs of electrons to put around it. The next thing you want to do is you want to figure out what the central atom in the molecule is. And to be honest, most of the time, it's the first atom listed. So in NH3, that's going to be nitrogen, all right? But here's a caveat. It's never going to be hydrogen. So water is H2O, but you don't want to put hydrogen in the middle. Hydrogen can only handle 1 bond. It doesn't have the power to be the central atom. So if you see H2O, you would put oxygen in the middle, but 99% of the time, the first atom listed is the one that goes in the middle. So it's going to be nitrogen in this case. So it's always, the central atom is always the atom which has the lowest interest, if you will, in electrons. And again, nitrogen's not a fair example here because it doesn't have it. But if you have a choice, you want the one which is less into electrons. We'll talk about this more later. But anyway, because it's usually the central atom, it's going to be the nitrogen here. Now, the next thing you want to do is you want to connect the outer atoms to the nitrogen, to the central atom. You don't want the hydrogens to float off into the void. You want to connect the hydrogens to the nitrogen. So we're going to draw a sigma bond, which is a fancy name for a single bond, between those hydrogens and the nitrogen. And that just keeps them from running off into the blue yonder there. Now, each of those lines we've drawn is a bonding pair. That's 2 of our valence electrons. And if you remember from before, we have a total of 4 pairs of electrons to place in this molecule. So we have used 1, 2, 3 of those pairs by drawing those bonding pairs. So again, there's a bonding pair, there's a bonding pair, and there's a bonding pair. We have 4 pairs total. We've used 3 pairs, and now we're good to go. Now, hydrogen can only handle 1 bond, so if you have any leftover electrons, they go on the central atom, and we do have 1 pair left over. That's going to be a lone pair. So we're going to put our last pair on the nitrogen, that little double dot thing right there. That's a lone pair of electrons, and that's only on the nitrogen. So pat yourselves on the back. You have drawn your first Lewis structure. Woohoo! I know you're excited. I am too. But anyway, ammonia has a nitrogen in the middle, hydrogens around the outside. It has 4 pairs total, 3 pairs to hydrogen, 1 lone pair. Nitrogen has an octet, which means 3 pairs that are bonding and 1 pair that's lone. So 4 pairs times 2 electrons is 8 electrons, the octet. Hydrogen only needs 1 pair, so it's happy too. All the molecule is happy. This is the Lewis structure for ammonia, NH3. The lone pair electrons on nitrogen do take up more space than a regular shared pair of electrons or bonding pair. So that lone pair is actually pretty big. It kind of has like a bigger footprint, if you will. And this will be important to us later on. So that lone pair is going to squish the other hydrogens a little bit more together. This might be important in things you talk about soon. So I just wanted to point that out. So in this molecule, you've got a big big thing of electrons, because electrons really don't want to be next to each other. They're negative. They don't get along that well. Bonding pairs are smaller. They're more concise. They get along better. So just keep this in the back of your mind while we go through this discussion. So here's a type of problem you might see, and it says, which of the following Lewis structures is or are correct? And to answer this question, you want to make sure that hydrogen has one bond, all right, and none of those structures have hydrogen with a lone pair or a double bond, so that's okay. But you also want to make sure that your central atom has an octet, and an octet in a Lewis structure means 4 pairs of electrons, and those pairs can be bonding pairs or lone pairs. So if you look at all of these, the nitrogen in the upper left corner, number 1, only has 3 pairs of electron around it. It has 3 bonding pairs, but it doesn't have that magic 4. So that would not be a correct structure. And the same thing here for the oxygen in that H2O. Oxygen has 2 bonding pairs to the hydrogens, but it needs to have 4 pairs. So I don't like number 1, I don't like number 2. Now, this fluorine in the HF molecule has a total of 3 pairs around it, 1 bonding and 2 lone pairs. But you need to have 4 pairs. Fluorine doesn't have 4 pairs either, so that would be an unhappy structure. However, if you look at the phosphorus in pH3, phosphorus has 3 bonding pairs and 1 lone pair, 4 pairs total. And things with 4 pairs are quote-unquote happy, which means stable. So that would be the correct Lewis structure. Everything has an octet. Phosphorus has its octet of electrons. Hydrogen has the 1 pair of electrons. It needs to have like a helium configuration. The other 3 don't have an octet, and they would not be considered correct. So this is a summary of the Lewis structure rules, and again, we went through it before and we'll look at some more examples, but in a nutshell, decide on the central atom and find the number of valence electrons. So the central atom is usually the first atom listed in a structure, but it's always the one which is less than 2 electrons, and it will never be hydrogen. So for NH3, the nitrogen is the central atom. For H2O, though, you don't want hydrogen to be in the middle, so that's going to be oxygen. And then the valence electrons, you just count them up from the group number. So in NH3, nitrogen was group 5. It had 5 valence. Hydrogen's group 1. It has 1 valence, and there's 3 of them. 8 electrons total are valence electrons for NH3, or 4 pairs. And then number 2, you want to connect those outer atoms to the inner atoms, which was making a single bond, all right, or a sigma bond. Those are covalent bonds because the electrons are being shared and stuff, no problem. Now in number 3, we didn't do this last time. You want to add lone pairs to the outside atoms first, so they get an octet, and then number 4, if you have any electrons over, put them on the central atom. Now in our structure with NH3, it didn't have any electrons to put on the outside atoms because they were just hydrogen. Hydrogen just needs a single bond. So we skipped number 3 and went to number 4 and put that remaining lone pair on the nitrogen in the middle part. And then 5, because nitrogen had an NH3 octet, we didn't have to do number 5. You can make double bonds or triple bonds if those central atoms need more electrons. And we'll see examples of all of this here coming up and in the problem set in the lab and all that jazz. But this is a nice summary of the structure, the rules you need to draw successful Lewis structures. Let's look at carbon dioxide. Now, carbon dioxide, the central atom, is almost always the first atom listed, and it certainly is never the atom which is more into electrons. Oxygen is definitely more into electrons than carbon. So we would say for this one, the central atom is carbon. It's the first one listed, it's not into electrons, blah, blah, blah. Valence electrons. Carbon is in group 4, so 4 valence electrons. Oxygen is in group 6, 6 valence electrons, and 6 times 2. So 4 from carbon plus 6 times 2, 12 from oxygen, means this thing has a total of 16 valence electrons. But we'll almost always divide them by 2 to find how many pairs there are. 16 divided by 2 would be 8 pairs of electrons. The next step, we want to put the central atom in the middle and the outer atoms on the outside. We're going to put the oxygens on the outside, connect them to the carbon through a sigma bond or a single bond. Now that's 2 of our pairs here we've used up. We have 8 pairs total, and we just drew 2 pairs making those connections to the carbon. So we have 6 pairs of electrons left. Now, the next thing, which we didn't do with NH3, but we're going to do here, we're going to use our remaining pairs to give the outside atoms an octet. And remember, an octet means 4 pairs of electrons. So we're going to put 1, 2, 3 lone pairs on each oxygen. Because with oxygen with 3 lone pairs and a bonding pair, that's 4 pairs total. That's giving oxygen an octet. And the other oxygen on the other side, same thing. 3 lone pairs, 1 bonding pair, 4 pairs total for an octet. So by doing this, we've used up all of our lone pairs. We used up 2 to make the sigma bonds, and with the lone pairs on this one, final structure down here, we now have no more lone pairs. Oxygens are happy, absolutely, but carbon only has 2 pairs, and that octet is really, really important. So carbon is not happy in this structure. So another rule on that list is that if the central isn't happy, you have to make multiple bonds, i.e. double or even sometimes triple bonds. So for this molecule, what we're going to do is we're going to share a lone pair on both the left and the right oxygens with the carbon. So you can see what happens there in the lower left-hand corner. The lone pair right there is being moved to a bonding pair between carbon. And we're going to do the same thing for this one right there. We're going to make a double bond. So the structure here now on the lower right, this is the Lewis structure for carbon dioxide. And if you look at it for octets, your oxygens have 2 lone pairs and now 2 bonding pairs. So they have a total of 4 pairs total. They're totally happy. But now carbon has 4 pairs, 4 bonding pairs, but carbon doesn't care. As long as they have that octet, that's really, really good. The second bond that we drew, the red lines right there, those are technically called pi bonds. So we made a pi bond between the outer oxygen and the central carbon. And the first line we drew, those are technically sigma bonds. So a double bond is technically a sigma plus a pi bond. And if you see that references, that's what it means. A double bond has 2 bonds. And in that double bond, the first one is a single bond or sigma bond, and the second one is a pi bond. So a double bond is a sigma plus pi. Once in a while, those things will come up. So now you know what they mean. A pi bond is like the second bond you put between the atoms. Carbon dioxide could have been written with a triple bond on the left and a single bond on the right. And that's very true, all right, because the carbons will then have, the carbon in the middle on the left will have 4 pairs just like the carbon on the right-hand structure, stuff like that. So a triple bond and a single bond is a possibility. These are called resonant structures of carbon dioxide. And a resonant structure makes the molecule more stable, believe it or not. So this crazy thing, the double bonds sometimes will rotate around. And you'll have a triple bond on the left and a single bond on the right, as in this structure right here. But then the triple bond goes back to the oxygen to make 2 double bonds, as in this structure right here. And once in a while then you can have the other form, which would be a triple bond on the right hand oxygen. So these 3 structures are called resonance structures, and resonance is a way to stabilize a molecule. And for better or worse, CO2 is a very stable molecule for this reason. It can shift the electrons around in those pi bonds. And there's a lot more that can be done with resonance, but I think I should introduce it here just real fast so that you know. So if you hear about resonance, it's always about moving a double bond into a triple bond or triple bonds into double bonds, something like that. They move around to make the molecule more stable. You can extend Lewis structure rules into how they look like in 3-dimensional space. Now, as a chemist, I can't draw very well at all. You can tell from my drawings in my iPad here that they're pretty bad. But that's the good thing about these rules. You don't have to be an artist. Now, if you are an artist, I love seeing your drawings, 3 dimensions. They're really, really cool. But for right now, what we're going to do is apply what's called valence shell electron pair repulsion theory. And goodness goodness, wasn't that a lot of syllables? Let's call it VSEPR, because that's a lot easier to say. VSEPR theory, 2 Lewis structures. Why would you do that, Dr. Russell? Oh, great question, random student in the back of the room. Valence shell electron pair repulsion, or VSEPR, allows the chemist to kind of visualize what the molecule looks like in 3-dimensional space. Like maybe they aren't flat, maybe they have 3-dimensional kind of structure. And what are the bond angles and stuff like that? So VSEPR is a super useful addition to Lewis theory, Lewis structure theory. And once you have a good Lewis structure, VSEPR applies itself really, really well. The big idea of VSEPR, like we've seen already, is that electrons don't want to be next to each other. Negative and negative charges repel. And if you have a lot of bonds running around, those are big sources of negative energy, and they're going to be as far apart from each other as they can. So we'll see this in a lot of these structures. All these structures we're going to look at are basically about electrons staying as far apart from each other as they can. That makes the molecule more stable and less likely to deconstruct and stuff like that, or decompose, stuff like that.
According to VSEPR theory, the valence pairs surrounding an atom move to positions that minimize their repulsions.
In this little video, each of those bulbous things represents a bonding pair between the central atom, which is in the middle of that kind of group of balloons, if you will, and the outside atoms. And you can see that each time you add a bond, they try and get as far apart from each other as they can. So first the two are basically like 180 degrees apart. Then as you add a third one, they were 120 degrees apart, then 4, 5, etc., etc. Now in Chem 151, we're just going to look at up to 4 pairs around a central atom, but you could do 5 and 6. And this is what VSEPR does. It tries to analyze where the electrons are and make predictions as to what the molecule looks like, stuff like that. So to apply VSEPR theory, first you got to start by drawing the Lewis structure, and that's not a problem once you do it a few times. But the next thing then, to apply the VSEPR, you need to figure out the number of electron clouds. Now an electron cloud can be a lone pair, and it can be a bonding pair to another atom. So lone pairs are easy to see, the little dots. A bonding pair to an atom can be a single, double, or triple bond, but they all count as one big cloud. And once you know the number of clouds, then you can predict the shape of the molecule by realizing they want to get as far as possible from each other. So it's not as bad as it might sound, although some of the names might be a little weird if you haven't seen this before. This is something we're going to use in lab to represent the different names of the pieces. And at the bottom down there is an example of NH3. Now when we drew NH3, it had a lone pair on the top and 3 bonding pairs to hydrogen atoms. So ammonia, NH3, has a total of 4 clouds. So if you look at this structure in the lower left, ammonia has 1, 2, and 3 bonding pairs to the hydrogens, and it also has a lone pair on top, that red thing. So we would say that ammonia has a total of 4 clouds, and in the bottom of this are the 3 possibilities you can have when you have 4 clouds of electrons. So to figure out which one NH3 is, you have to realize that 3 of them are connected to bonding pairs, or bonds in this case, and 1 of them is a lone pair. So once you realize that, then you can just plug and chug basically the answers to the right of that. So we would call the electron pair geometry, or EPG, to be tetrahedral, because in reality NH3 takes on a tetrahedral shape. You get more separation between the lone pairs and those bonding pairs as you get to a tetrahedral arrangement, which is really interesting. Now, the molecular shape, which is shown there on the right-hand side, is what the molecule, quote-unquote, looks like without the lone pair electrons showing, because electrons are just shimmering things of energy, more or less, so we wouldn't probably see them if we could shrink down to that level. Molecular geometries can be helpful, and it's a cool thing to know. Molecular geometry for this thing is called trigonal pyramid. It's what the molecule looks like without the lone pairs. They're there, and they're having an influence influence, but they're not actually seen in the molecule. We also have the bond angles. Anytime you have a tetrahedral system, it's going to be about 109 degrees. And finally, polarity is going to be something which is important to us. These systems are always going to be polar, and I'll talk about that here in a little bit. But the important part for this discussion is that first, when you're doing VSEPR geometry to a Lewis structure, you've got to figure out the number of clouds. And clouds means number of lone pairs plus number of connections essentially to atoms. So in NH3, there were 3 connections to atoms, 3 bonding pairs, and 1 lone pair for 4 clouds total. So that's why we're going to use this particular row right here. And that means the EPG is tetrahedral, the MG is trigonal pyramid, and the bond angles are 109. And we'll talk about polarity here in a little bit. So this is ammonia, the Lewis structure we drew, and we can interpret this now according to VSEPR geometry. Now again, remembering that we need to figure out clouds, this has 1 lone pair, which was that big red thing kind of on the top in the last version, 1 lone pair, and 1 and 2 and 3 bonding pairs. The outer atoms are connected to the nitrogen 3 times. So this is a 4 cloud system, 1 lone pair and 3 bonding pairs. So if you look back at that sheet, this is where the tetrahedral part comes from. It's really a tetrahedron, but it's a tetrahedral geometry, whatever. Anyway, electron pair geometry here is called tetrahedral, all right? And that's the idea. So when we drew the Lewis structure, you can notice by the lines, we just drew like left and right, up and down, 90 degrees and 180 degrees. And that's not at all what this molecule looks like, because you can do better than 90 degrees if you go to a tetrahedral environment. Tetrahedrons the angles are about 109, and the electrons want to be as far apart from each other as they can. So we would say that ammonia has a tetrahedral electron pair geometry. On that same thing, we also talked about molecular geometry, which is what the molecule looks like where the lone pairs are present, but they're not actually observable. So in the structure on the right, which is rotating there with the blue nitrogen in the middle, that's the molecular geometry for this molecule. It's called trigonal pyramid. That lone pair is up there, but it's not being seen. All right, it's having an influence. It's pushing those hydrogens down, but it isn't actually being observed in the molecule. So when you're doing VSEPR, usually you can get then the electron pair geometry, which here would be tetrahedral, the molecular geometry, which here is trigonal pyramid, and on that sheet back there, you can see that these are all 109 degrees. That thing in the lower right there is just another example of ammonia just rotating around. It's kind of interesting to think about the possibilities, how this thing reacts, stuff like that. So this is how you apply VSEPR to a Lewis structure. Let's test ourselves here, and let's describe the Lewis structure, electron pair geometry, and molecular shape of methane. So what we would do here is, first of all, find the Lewis structure for CH4. We'll build it, and once we do that, we can figure out the number of clouds around the central atom and number of bonding and lone pairs to find the EPG, electron pair geometry, the MG, or molecular shape, molecular geometry, and we can even find the bond angles here for methane, CH4. Now, I'm going to try and do this kind of quick and dirty here on my iPad. So CH4 we're going to find the valence electrons. Carbon is 4, hydrogen is 1, and there's 4 of them. So 4 plus 4 is 8 valence electrons, or 4 pairs of electrons in CH4. That's all we have to deal with. We need to find the central atom. It's usually the first atom listed, never hydrogen. So in this case, that's easy. It's going to be carbon's going to be the central atom. And we need to connect those hydrogens to the carbon. So we're going to draw bonding pairs that connect them, like a chain, if you will, to keep the hydrogens connected to that carbon in the middle. And if you look there, I drew 4 lines. Each of those is a pair of electrons, and I only have 4 pairs, so I'm out of pairs of electrons. So I have just drawn the CH4 Lewis structure. All right, it's carbon in the middle, hydrogens around the outside. Carbon has an octet, 4 pairs around it. It's happy. Hydrogen has its 1 pair. It's happy. All right, Lewis structure, good to go. Okay, now for the VSEPR part, which is electron pair geometry, molecular geometry, etc., we need to find the number of clouds around the central atom. So we're going to look for carbon here and see how many clouds it has. Now around carbon, there's 1, 2, 3, 4 pairs of electrons, 4 bonding pairs technically, and each of those is a cloud. So there's 4 clouds around the carbon, and all of them are bonding pairs. So if you look back on that list where there's 4 clouds, 4 bonding pairs, and 0 lone pairs, you'll see that the EPG is called tetrahedral. Again, I can't draw worth anything on this, so anyway, it's embarrassing. But anyway, you get the idea. The EPG, electron pair geometry, is called tetrahedral. The molecular geometry, which is also called molecular shape sometimes, same thing, is also tetrahedral. If there are no lone pairs on your central atom, EPG and MG are the same thing. And even though it doesn't ask for it, if you look on that table, this is 109 degrees is the angles and stuff associated with tetrahedrons. So this is your instructor's really bad version of drawing this problem. Electron pair Lewis structure was CH4, carbon in the middle of hydrogens, EPG tetrahedral, molecular geometry, which is the same as molecular shape tetrahedral, and even though it didn't ask for it, the bond angles are 109 degrees. Now, this is a version where the drawings are a lot nicer than your instructor's poor handwriting, so bear with it. But anyway, the valence electrons, carbon is 4, hydrogen's 1, and there's 4 of them. So that's where the 8 comes from, 8 valence electrons. We usually divide the valence electrons by 2 to get 4 pairs. Carbon is the first atom listed, so probably that's going to be the central atom. Hydrogen can never be the central atom, so that makes that easy. Carbon is in the middle of the 4 H's. We drew bonding pairs to connect them. So carbon had 4 bonding pairs, no lone pairs, when you drew the Lewis structure. And if you look on that table, the EPG, electron pair geometry, for something with 4 clouds, 4 bonds, and no lone pairs, tetrahedral. And the molecular shape or molecular geometry, same name, is also going to be tetrahedral. If there's no lone pairs on it, then it's the same name, which is kind of nice. And it didn't ask for it, but the bond angles would be about 109. But what is kind of cool here is this drawing. You can see a better version of what the tetrahedral actually looks like for CH4. It's not like up, down, left, right, which is how I drew my Lewis structure because I can't draw. In reality, it's a tetrahedron. The angles are 109. They're all evenly distributed. Those bonding pairs are as far apart from each other as they can. And that's why the VSEPR rules are so cool. In that VSEPR table that we looked at earlier, there was a mention about polarity. Some things were always polar. So let's talk a little bit more about what it means to be polar and nonpolar. If you have 2 atoms connected with a covalent bond, they're each going to want electrons to some degree. And if the 2 atoms in the bond are the same, i.e. if H and H are in a bond, or Cl and Cl, or O and O, stuff like that, they're going to pull evenly, and that's referred to as a non-polar bond. And non-polar bond just means that the electrons are equally on both sides of that bond. So in the case of H2, you'd have just as much electrons on the first hydrogen as you would the second hydrogen. And if it was O2, you'd have just as many electrons on the first oxygen as the second oxygen. So non-polar means the electrons are distributed well. However, what happens almost all the time is that you have 2 atoms that are sharing a bond that aren't the same. And then you're going to have, like, for example, one will be more into electrons than other. So in HCl, chlorine pulls electrons a lot more than hydrogen. So if you look at the electrons overall, chlorine has more electron density around it than hydrogen. And the same thing with HF. F is more into electrons, it pulls more than hydrogen. So most bonds will have uneven unequal distribution of these electrons. And these are technically called polar covalent bonds, and they're very common. Most bonds are going to be polar, all right? And if you're having trouble thinking about the electrons, then think about a piece of bread, and you're going to put peanut butter on it. And I love peanut butter. It's one of my weaknesses, but this is a lecture, not my weirdness. So anyway, if I'm going to spread peanut butter on my piece of bread, and I spread it evenly across the whole piece of bread, that would be an example of nonpolar. All the peanut butter is distributed evenly over the bread. But what happens is I get hungry and I get lazy, so I kind of slop some peanut butter on, and I end up with more peanut butter, say, on the right side of the bread than the left side, or vice versa, whatever. That would be an unequal distribution of peanut butter. That would be an example of a polar situation. Now, of course, instead of lovely peanut butter, we're going to have electrons, which aren't as exciting to eat, but in terms of chemical reactivity, it's actually very, very important. So if you have more electrons on one side than the other, you're going to have some differences in how these things react. So most bonds are going to be polar because they're not the same, but there are some exceptions when they are the same, like H2, Cl2, stuff like that. I always hate to say this, but it's true. If you have to guess, most things are polar, but I am going to show you some nonpolar things too, so that's not surefire. Here's an example of the HCl molecule, and as I said earlier, chlorine is more in 2 electrons than hydrogens. So what that means is there's more peanut butter around the chlorine than the hydrogen. Now again, I got to get away from peanut butter. I'm sorry. This is about electrons, Michael, not peanut butter. You must be getting hungry. All right, Prof. Hat back on. Chlorine is more into electrons, so it has a slight negative charge. And that little symbol there to the left of that negative sign, that's a lowercase delta, a Greek letter. So delta negative just means it has a partial negative charge. Now, it's not a full-on negative like chloride, Cl minus. That's got truly a negative charge. It's just trying to say that it has more negative electron density around it than hydrogen. Hydrogen doesn't pull as well. It's going to have a slight positive charge. So you can see in that drawing underneath there, the chlorine side, that kind of orange looking thing on the right, there's a lot more bulbous part. That's trying to show where the electrons are. Chlorine has a lot more electron density around it, so it gets a partial negative charge. Hydrogen is not into electrons as much. It doesn't have as much bulbous part. It's a slightly positive charge. And this is really important when it comes to reactivity. Now in HCl, like we talked about earlier, hydrogen is not as much into electrons. It gets the partial delta sign, the partial positive charge. And chlorine is more into electrons, so it gets the delta negative sign. It's more into electrons. It's going to have more electron density around it. This leads to the idea of what's called electronegativity, which is literally a scale as to which atoms are most into electrons and most elements are least into electrons. And I'll show you the scale here in a little bit. But the important part to remember is that fluorine, number 9 on the periodic table, is more into electrons than anything else. It has a value of 4, which is the highest electronegativity value. So fluorine will always be that delta negative like chlorine is down there with any other atom, unless it's fluorine itself. So fluorine loves electrons, and most of the other elements don't like the electrons as much as fluorine does. Here are some values for electronegativity, and you can see at the top right-hand corner right there, fluorine is 4. It's the biggest one, and that just shows that it's more into electrons than anything else. Now, oxygen is number 2. It's got a value of 3.5. Not as much as fluorine. Fluorine's got a 4 value, but pretty high. And then nitrogen and chlorine are tied for number 3. They both have a value of 3, so they're also into electrons a lot. And you can see how it kind of goes down and down. Little rubidium in the lower right-hand corner on this scale is really not into electrons. 0.8 is a smaller value. That means it would more likely be positive than negative. On the other hand, fluorine is positive 4. That's really into electrons. So the bigger the number, the more into electrons the element is, and the smaller the number, the less into electrons they are. Now again, notice the noble gases are not part of this table. They don't usually make compounds, so they don't really have an electronegativity value. Most of the noble gases just sit there and don't react. We'll talk in a future course about some of the compounds that can be made with periodic or with the noble gases, but they're rare and they're not as exciting. You can have polar bonds, but your molecule can still be nonpolar. And this is kind of a trip. So the entire molecule is usually going to be polar for most of these. You're going to have unequal distribution of electrons. However, you have to think about all of the interactions of all the bonds to figure out if the molecule is polar or nonpolar. So the entire molecule might have more electrons on one atom than in another part of the molecule. And again, polarity can be really helpful when it comes to thinking about how molecules react, stuff like that. These are some pictures of molecules, water on the left and a compound called chloromethane on the right. And it shows essentially where the electrons hang out on these molecules. And water, H2O, you can see that the oxygen has a lot of electron density next to it. Those two little delta negatives right there are places that there's a lot of electron density. So when it comes to water, water has a partial negative side by the oxygens. But I also want to point out the hydrogens right there. They have partial positive charges by them. And so they're not into electrons as much. They would prefer to be positive. So in a nutshell, water is very polar. It has an unequal distribution of electrons. It has a lot of electron density by the oxygen, which is that red atom there. This is big time negative. On the other hand, by the hydrogens down there, you've got positive charge. Now, it's not full on positive, full on negative. Technically, it's the partial negative on the top and a partial positive on the bottom. But water's ability to be polar is one of the things that makes it really exciting as a chemist in terms of reactivity, and we'll go over that in a future lecture. Now, CH3Cl, those hydrogens don't pull as much as chlorine. Chlorine is one of the high electronegativity elements. So the chlorine in that molecule is going to have a negative charge. So most of the electron density is going to be around that Cl in the molecule. On the other hand, down here by these hydrogens, they're going to be not have as much electron density. I don't want to say stripped of electrons, but they won't be into electrons as much as the chlorine. So the positive part of this molecule will be down here, and the negative part will be up here. So we could write delta negative, and this would be a delta positive. Both of these molecules are considered polar molecules. Also notice this term down here, asymmetric. If your central atom is connected to different things, and both of these molecules are, it's asymmetric, and they're always going to be polar. So in terms of water, around the oxygen there, you have 2 lone pairs and 2 hydrogens. That's asymmetric. It's not the same stuff. Like you don't have 4 hydrogens around it, or you don't have 4 lone pairs. You've got a mix of 2 lone pairs and 2 hydrogens. That makes water asymmetric, and that makes it polar. Now, chloromethane there is also asymmetric. Around the carbon, you have 3 hydrogens and 1 Cl. So you don't have all the same stuff. Like you don't have just hydrogens or just Cls, but it's a mixture of H and Cl. That makes it asymmetric, and that makes it a polar molecule. You've got more electron density in the top than you do on the bottom. Here's some examples of molecules which are symmetric. And again, symmetry in this case means that everything around the central atom is the same. So there's carbon in the middle of CO2, and oxygen pulls super hard. It's number 2 on the electronegativity scale, only second to fluorine. So that means oxygen is just ripping electron density away from the carbon. But the oxygen on the right, its pull is canceled by the pull of the oxygen on the left. So again, everything around that carbon is the same. You've got a double bond on the left and a double bond on the right. So CO2 is a non-polar molecule. It's symmetric, and that means there's not really an unequal distribution of electrons. And that thing on the right there, which is called carbon tetrachloride, carbon has only chlorines around it. Now, chlorine pulls really hard too, almost as strong as oxygen. But again, everything around the carbon is the same. It's a symmetric molecule, so there's no polarity associated with CCl4. We would call CCl4 a non-polar molecule. So to summarize these last two slides, if everything around this central atom is the same, like just double bond O's, just CCl bonds, just, CH bonds, or anything like that, if everything is the same, it's going to be nonpolar. But if even one part is different, like a lone pair and 3 bonds to atoms, or maybe you'll have 2 chlorines and 2 fluorines, or something like that, if everything around the central atom is not the same, then it's going to be polar. And finally, if you have to guess, most molecules are polar because they don't have the symmetry of the nonpolar molecule. So I always hate to say these things, but if you have to guess polar. Here are 3 molecules, and I'd like you to think about if you think they are polar or nonpolar. And what we're going to do is look to see if they are symmetric or non-symmetric. So let's look at BF3 on the left. Now that boron, which is the red atom, has 3 fluorines, the green atoms, all the way around it. And that boron has only fluorines. There's no lone pairs, there's no hydrogens connected to the boron, there's no oxygens, there's no uraniums, whatever. So everything is the same around the central atom. That's a symmetric molecule because boron only has fluorines around it. And symmetric means it's going to be nonpolar. So BF3 would be an example of a non-polar molecule. Now, the next one, Cl2CO, carbon's in the middle. Carbon's less than 2 electrons than chlorine, by the way. But anyway, carbon in the middle has an oxygen above, the red one, and 2 Cls, one to the left, one to the right. But important thing for us, everything around that carbon is not the same. It's not just chlorine, it's not just oxygen, it's a mixture of chlorine and oxygen. So this is an asymmetric molecule. Everything's not the same around it. That's going to be polar. All right, that thing definitely has a polar moment. Now the last one, NH3, at first looks like it's symmetric, like there's hydrogens connected to the nitrogens, and it looks like it would be symmetric, everything's good to go. But you have to be careful because sometimes lone pairs are not shown. That's the molecular shape or molecular geometry for NH3, and a lot of times they won't show the lone pairs. So that nitrogen has more than just hydrogens around it. It has 3 hydrogens and a lone pair. That lone pair breaks the symmetry. It's an asymmetric molecule, and it's going to be polar. So be careful of the lone pairs. Sometimes they don't show up, but a lone pair will also break the symmetry, making it polar overall. And again, I hate to always say it, but if you have to guess polar. But that being said, that far left one was symmetric. That's going to be a non-polar molecule. Okay, that's it for this lecture over Chapter 4, Sections 4.4 to 4.6. I hope it helped. If you have any questions on anything, feel free to reach out to me via email. You can also talk to the LSC/Avid Center above the library. They can help too. I know you can do this stuff. I'm rooting for you. Have a great day. Thanks for joining me, and thanks for being here.